A different number of lanes example. A lot of the same information was given to you in the previous example I've done, so we'll go through this pretty quickly here. Now, let me just point out a couple of things. Peak volume is 630 vehicles per hour, 60 miles per hour road. Peak hour volume, familiar road, so we're going to use a 1. The difference here is the information is given to you about the road as it is going uphill. So it's a 4.5% incline, and this incline happens for about 4,224 feet. Then here's the traffic mix. So within the traffic you have a certain number of passenger cars, and then you have 10% of those vehicles in the traffic or trucks, 10% of buses, and 15% of RVs, and the rest are passenger cars. So we have to determine the number of lanes that's required to be able to accommodate this traffic mix at a level of service C. Right off the bat, I'm going to go ahead and tell you that you're going to need a couple of different tables. So here are the 3 different types of tables you're going to need. It's a table for upgrades, trucks and buses on specific upgrades. This is passenger car equivalencies for RVs for specific upgrades. And then we'll even modify the questions so that we'll use the downgrades as well for the trucks and buses. So those are the 3 that you're going to be using. Okay, in order to sustain a level of service C at 60 miles per hour, I am going to need a maximum service flow rate of 1550 as shown here. Also, that can be seen here, whereas the boundary for level of service A ends here, level of service B ends here, and the boundary for level of service C ends here. And so at 60 miles per hour, at its boundary, if I draw a straight line down, that would also give me that 1550. And that's pretty much what I wrote right here. Everything else was given to you except for the heavy vehicle factor, which is what we're going to be calculating next. Real quick, this is the equation for the heavy vehicle factor. I've detailed some information for you to know exactly what each one of these variables mean. The heavy vehicle factor is basically used to translate any vehicles, all types of vehicles in the traffic mix, so that all of the vehicles are represented in passenger cars. And all you do is just take the vehicles and divide it by the heavy vehicle factor. So we're trying to use these variables to come up with a factor that would allow us to use the number of lanes equation. This is the decimal percentage for trucks and buses. And this is a decimal percentage just for RVs. We have to find these equivalency factors from tables. So let's go ahead and do that. The problem stated that we were going uphill, incline, upgrade, for 4.5 at a 4.5%. So I'm in between 4 and 5 here. And this goes up to 5, and this is greater than 5. So if you had a 5.1, of course you'll be using this, but this is 4.5, so we know we definitely are here. And then it said it did it for about 4,224 feet. I know that is more than half a mile, so I know I'm not only in this row, but I know that I'm in this column, and specifically in that row within the row. So I know that my E sub t, this is E sub t, or actually this is going to be E sub r, it's going to be 2.5. That's what I'll be using. To figure out what my E sub t is, I have to apply the same thing, just make sure that I am using the correct table for upgrades and for trucks and buses. At 10% trucks, 10% buses, so 10 plus 10 is equal to 20. So I'm on that column, and I'm in this row within this row because the 4,224 is equal to about 0.8 miles. And so we're going to be using a 3.0 for my E sub t. So here's a solution for going uphill. I put my equivalency factor for my trucks and buses here. equivalency factor for my RVs here and my percentages, and I end up getting 0.61538, and I'll use that in the number of lanes equation. Here we are, just added that number, that 0.615, into the number of lanes equation. So now I have my heavy vehicle factor incorporated, and really, if you remember, all I've done is I've turned the number of vehicles into passenger cars just by dividing vehicles by the heavy vehicle factor. Now this entire thing is in passenger cars per hour, and so is this. This is in passenger cars per hour. That's actually given to us in passenger cars. So now we have one unit being represented, which represents the number of lanes that are required. You might be noticing that this 0.38 and what that means. That just means you definitely need more than one. One wouldn't do it. This also means, since you're going uphill, maybe you can think about it this way. If you're traveling uphill and you only have one lane, however, that lane, not only did it have vehicles or passenger cars, but you also had trucks, maybe 18-wheelers. You also have buses. And you know, if they're in that traffic stream mix, and you might have a little small vehicle here, they're going to slow vehicles down. So sometimes what you would see is something called a truck climbing lane. All right, so this is a truck climbing lane. And that's just a lane that is, it's an extra lane. It just looks like an extra lane, but those are the lane. This lane right here is primarily used by trucks when they are traveling uphill for long distances, because they cannot travel at the same rate and speed as passenger cars. And so if they are no longer in that traffic mix, then the operation, and you kind of move them over here, the operation and the flow of the vehicles on this lane would just be that much better. And so to maintain a level of service C on that roadway, you would definitely need one lane, but you probably need to do a little bit more than just one lane, and that could be in the truck climbing lane. Now, if you happen to be curious like me, then you might be wondering, what would happen if we were to change something in this example problem? What would happen if we were to change upgrade to downgrade, and incline to decline? So now it's not going uphill, it's going downhill. And so the number of lanes required on the decline section of the road to sustain a level of service C is the question that's being asked now. How would that change? Would the number of lanes increase or decrease if we were to do this? Well, one thing we know would change, since we're not traveling uphill and vehicles are no longer slowly climbing uphill, especially those trucks and buses, then we may have a different heavy vehicle factor. And so I just changed a couple of things here. No longer downhill, which means that I'm going to use a 1.5 here, and I'll show you where I got that from. This right here is your trucks and buses on specific downgrades. We could have used either one of these two in a row. We know that the length is going to be closer to a mile than it is going to be closer to 4 miles. And we know we have 20% here, so 1.5 is what we're going to be using, and we did. We also use 1.2. And 1.2 is always going to be the assumed value for RVs going downhill. So it doesn't have a table because we assume that it's 1.2. So this is always for RVs only downhill. So with that, we ended up calculating that the new heavy vehicle factor for downhill is going to be equal to 0.885. And so that number is going to be placed in the new number of lanes equation. See what happens. And so here we have it. Just put the 630, same as up there, 1550, same as up there. Peak hour factor is the same, so the only difference here is going to be your heavy vehicle factor, because of course the familiarity factor is going to be 1. That's not going to change anything. So we've gone from 1.38 down to a necessary 0.95 lanes. So that means after you get up to the crest of the hill, you can start transitioning these trucks back over, because now all you're going to need is one lane going downhill.